And the proposal submission deadline is August 1st.
By the way, just linguistically, you do know that you really meant 1x per row.
No, I meant 1x per column.
Really? Yeah.
Yeah.
Oh, that makes sense.
Because I did 1x per row, I got it wrong.
All right, here we go.
I get it. All right.
All right.
That's-
Hi, Randy. Dan, I'm going to introduce our guest speaker now, okay? Dr. Adam Bergosser is an associate professor of physics at UC San Diego and an observational astrophysicist investigating the lowest mass stars, the coldest brown dwarfs, who were in Maleficent. You can see them at the archive. And exoplanets. His research, I can't read, that's too dark. Just give me 1 second. His research
Under the light.
This is here. This is it. His research includes a variety of ground-based and space-based resources to research the atmospheric properties and the processes of these objects, identifying and characterizing low-mass multiple systems, investigate magnetic activity, and use ground dwarf populations to study the Milky Way system. He also conducts physics education research, integrating creative, artistic, and embodied practices into physics learning, and has created several astronomy art-related installations in San Diego through his Project Planetarium. He earned his PhD from Caltech. In 2001, was a Hubble and Spencer postdoc fellow, and was on the faculty of MIT before coming to UCSD, gaining their loss. His legacy includes the Adam J. Bergosser Endowed Chairs for Astrophysicists, which is a Hughes chair for those who are interested. As we like to say, twinkle, twinkle, little star. Please welcome Dr. Adam Bergosser.
Thank you very much. So before I started, since you were talking about outreach, I wanted to do a little shameless promotion of my outreach coordinator. I want you to meet Diana Cowan. Last weekend, she was awarded the Flame Challenge winner at the World Science Festival in New York City. The Flame Challenge is something that Alan Alda started a few years ago to communicate science to 11-year-olds, right? So sort of junior high, middle school kids. And she won this competition. 27,000 people voted. 27,000 11-year-olds voted for her video, and it's online. So if you want to learn more about what she's been doing, it's been really fantastic, and I'd like you to get to know her because she's doing some fantastic work. So I'm going to talk about now my more scientific work, and talk about a new class of objects that we've just found in about the last 15 or 20 years. These are things that we'd never seen before, but as I'll say, we had sort of theoretically hypothesized that they exist, but they've only come into actual awareness in the last 10 or 15 years, 20 years. And these are brown dwarfs. And to give you a little bit of context, I wanted to start looking up at the sky. So if you're here in San Diego, this is something you'd see if you had a long exposure photographic picture. This is actually some artwork by Fernando Ramirez. And this, I think, is taken up in Palomar Mountain. And even here in San Diego, if you get out in the mountains, you can actually see quite a lot of beautiful structure up in the sky. And this particular structure here is the Milky Way galaxy. So you mentioned the Milky Way system in the introduction. Here's the Milky Way galaxy. Who's seen the Milky Way galaxy somewhere, sometime in their lives? Okay, good. More than most. I do this in my classes, and I'll have like 1 student out of 50 raise their hand, which is scary. But this is pretty good. But of course, you can see this is a night picture, but it looks really bright on the bottom here. Most of this is light pollution from San Diego and Los Angeles. If you get out to a truly dark spot, and this is taken out in Colorado, you see just a beautiful star field. And you start to see that there's a lot of variations in the stars up there, both in their brightnesses, and you can start to see that there's maybe a little variation in colors. Now, this is actually what Galileo would have seen back in the 17th century, and then he's pointing a telescope at the sky, and then you start to see even more structure, more beauty, more variation in the stars that are out here. This is a picture from a survey called the Sloan Digital Sky Survey. This particular survey mapped the entire, about a quarter of the sky from one telescope in New Mexico. Very, very deep images, and you start to see all these beautiful stars in lots of different colors. And just to take it to an extreme, many of you may have heard of the Hubble Deep Field or the Hubble Ultra Deep Field. This is the Hubble Extreme Deep Field. I think the next one will be the Hubble Overwhelmingly Deep Field. I'm not quite sure. This is a tiny patch of sky. This is about 1/100th of a degree on the sky. If you were to look at the moon's about 1/2 a degree on the sky, so it's a tiny, tiny piece of the sky. And in this tiny, tiny piece, we stop seeing individual stars and we start to see individual galaxies, and particularly galaxies that go back to the very beginning of the universe, very original formation of the universe. My point is that even though these are different objects, galaxies instead of stars, the light that we see is still starlight. All of the light that we see in the universe comes from stars. They are the light bulbs of the universe. And so each of these, sort of fuzzy patches is a collection of 100 million or 10 million or 100 billion, depends on the size of the galaxy, of individual stars that combine to make the light in this galaxy. So if you want to know anything about the universe and you want to look at it, what you're always looking at is starlight in every case. But not everything in the universe is visible. And so what's hidden? Many of you may know that, in fact, we astronomers have done a terrible job at looking at the universe because all the stuff that we know about is normal matter, things like stars and planets and people and ice cream and stuff like that. That's only 4% of the stuff in the universe. The other 96% is stuff we don't know what it is at all. Right? So the bulk of it is this stuff called dark energy, and maybe you know that a couple of years ago, a few physicists here, particularly in California, Saul Perlmutter is up at UC Berkeley, got the Nobel Prize for realizing that there is this energy, this pressure in the universe that's causing it to expand and accelerate in expansion. We call that dark energy. We call it dark energy because we have no idea what it is at all. Right? We're still trying to figure that out. And that may be 75% of all the stuff that's in the universe. Right? So they got the Nobel Prize just for figuring out that there's something that we don't know out there. It's pretty good. There's this other section over here, which we call dark matter. We call it dark matter because we have no idea what it is. All right? But it's different from dark energy because of energy and matter. It's because we know that dark matter is something that interacts with through gravity. It can pull on things. We can see this in how we measure stars going around galaxies, how fast they go around galaxies. We realize there has to be a lot more matter out there than we see in the starlight. And that's something like 5 times as much as this normal stuff like stars. That hasn't gotten a Nobel Prize yet because we still don't know what it is, but that's up for grabs. All right? So the story I'm going to tell you today is one of the trails to identify what this dark matter stuff is. And I'll give away my result. It failed. All right? What I'm going to talk about wasn't in the end dark matter, but it turns out this population that we thought might be dark matter is a very interesting population that's teaching us all about what stars are, what planets are, the difference between those, and what the actual contents in our galaxy are. So just to give a little more context on this, so that's the question, what is dark matter? So just to give a little context on this, when we look up at those pictures of the stars, we see different colors, different brightnesses. It turns out stars do come in different sizes, different temperatures, different masses. And so this is just a picture from Wikipedia showing kind of roughly what the main classes of stars. We classify stars based on what their spectra look like, what their sort of light structure looks like, what kind of molecules are in the atmosphere, et cetera. And we know that there are these really very big, bright, hot, massive stars called blue stars, 10 times bigger than the sun, 40 times more massive, 5 times hotter. And then there are very little stars that we call M dwarfs. I can go into all sorts of why this is not in alphabetical order. Maybe that'll be another talk later on. But those are very tiny little stars, 10% the size, 10% the mass, and half the temperature. Our sun is somewhere in the middle here. It's actually a G2 dwarf, in case someone asks you that in a bar. All right, G2 dwarf, remember that. All right, so let's go back to this picture. So these stars have different sizes. They have different colors. The cooler stars are red. The hotter stars are blue. That has to do with the physics of how light comes out of these things. And if we go back and look at this picture I showed earlier from the Sloan Digital Sky Survey, it should be pretty clear that unless I tweak this image in some way or the projector is sort of funny, a lot of these stars are red, which means a lot of these stars are cool, low-mass things. And in fact, something like 3/4 of all of the stars in our galaxy are the little tiny red ones on the left there. Most of the stars in our galaxy are tiny ones. We're actually kind of on the big end of this scale. Right? So 75% of those are red. Now, this was recognized many, many years ago, 50, 60 years ago. And in fact, there was a paper by this gentleman named Edwin Salpeter, who's made many fundamental contributions in astronomy. But one of the things he noticed is that if you go out and you actually count the number of stars, and you count them by what their masses are, what you find is exactly what I said, that most of the stars in our galaxy are these really tiny little ones. And so this diagram shows this. What it's showing is on the bottom is the mass of the star in log units, and so I just kind of put the different types in there so to give you an idea. Low mass stars on the right, high mass stars on the left. And then the vertical axis here is a measure of how many stars there are in the galaxy, like density of the stars. And each one of those steps is a factor of 10. So it goes up really quickly. So this is a power law. You may like remember Moore's law and sort of technology. That's a power law, how things double over time. What he found was that there's lots and lots of these little stars. And one of the things astronomers love to do, or physicists love to do, and scientists love to do, if they see a line, they just want to take that line and take it all the way as far as they can go. So if I just take that line and keep going to lower and lower masses, all the way down to maybe the mass of the planets in our solar system, like Jupiter, what you find is that you can actually make up all of the dark matter that we're missing in the low mass end that we can't see on this diagram, or at least they couldn't see back in the 1950s. So this kind of started the idea that maybe these tiny stars are this missing amount of dark matter. And they're dark because they're tiny, right? They're just they don't emit a lot of light. So if we look hard enough, maybe we will actually see them. All right, so that was the idea back in the 1950s and 1960s, and it started a whole field of research in this, which we'll talk about in just a moment. But I want to go take a step back and also explain why we think these stars are little and how we might expect those stars to actually look like based on how they form. So I'm going back to this picture from San Diego here, in this Milky Way galaxy that we see. We're actually looking right through the plane of our galaxy, right? We're sort of in the galaxy, so we're looking through it. And again, if you can see this on your own, you'll see that there's these dark patches in this Milky Way. It's not all light. Sometimes there's sort of dark stuff. These are massive, massive clouds that are in our galaxy, right? Many, many light years across. And these are the source of the stars. These massive clouds, under their own gravity, collapse and form the stars. And so this is kind of a cartoon picture of that process. So you start up in the upper left here, you have something that's a really massive size. And I have this unit, this length unit, 200,000 astronomical units, that's what AU means. An astronomical unit is distance from the sun to us. So 200,000 times that is the size of one of these clouds. Huge, massive cloud. And what happens is it just falls in, just collapses on itself. And as it does so, it starts to spin up. It starts to make a little disk of material around it, and that disk eventually sort of dissipates and makes the planets in its place. And what you end up in the end is a star and a collection of planets like we have here in the solar system. This process takes about 1 to 3 million years. It's relatively fast in astronomical speak, incredibly long for a graduate thesis project, okay, for example. So how do we know this? Well, what we do is we look out in the universe and we look at different areas of different ages. And so this is the cartoon picture. This is real data. And we see exactly the same kind of thing. So up in the upper left here is the sort of head of a nebula called the Eagle Nebula. If you're a fan of the Hubble Space Telescope, this is one of the first sort of amazing pictures that the Hubble produced of this Eagle Nebula, this cloud of material. And that cloud is starting to form stars. In fact, you can start seeing some of them poking out in the little red light here in the corner there. That's starting to collapse and form clouds. The next picture is one of those clouds that's now collapsed down and is starting to form a little disc-like structure. We call those propylids because they kind of look like frog propylids. The thing next to that, which looks like something you'd see out of Star Wars, some kind of death ray, is actually a star where the middle is blocked out by the disk of cloud and gas that's around it, going around it. And what we're seeing is sort of jets of material coming out the side. It's a very energetic phase of star formation. I'll just say that this last photo, this came out just 2 months ago. This is from a new instrument that's installed in the Gemini Space Telescope. That is a picture of the ring of material around the star. The star itself has been sort of subtracted off, and you see this perfect little ring of material around it. That ring of material is starting to form planets. And then, yeah, this last picture, this is a picture taken with the Keck telescope, and this is an image of another planetary system. Those 4 little dots that are going around there, which are probably a little small, hard to see, are 4 planets, and we actually have enough measurements to know that they're in orbit, they're going around the star. This is a picture of another planetary system. This didn't exist 4 years ago. Now we have these pictures of other planetary systems that we can study directly. Yes, please.
How big are those planets?
Good question. So these are very massive planets. They're about 7 times as massive as Jupiter, and Jupiter is about 1,000 times as massive. So these are big, big, big planets, very hot planets. We have nothing like these in our solar system. And that's one of the surprises we're finding in the exoplanet field, looking for planets from other stars, is planetary systems are different. They're very different from our own solar system. So but that's not something to talk, unfortunately. If I had 4 hours, maybe I could talk about that. All right. So anyways, this picture of star formation is sort of how we see how places like the Earth come into existence. Right? They start with big clouds. You end up with a star with planets around. Now that start from the big cloud to something like a star, it's a big jump in size. And when you get something like that big that shrinks down to the size of a star, there's many factors of 10 shrinking down in size. You're taking a lot of what we call gravitational potential energy, the potential for gravity, and turning that into heat. Right? It's the same thing if I took this fork here and I drop it on something, just drop it on the table. All right, if I drop it, I'm dropping it and I'm taking gravitational potential energy and turning it into sound energy. Right? That's kind of what happens in this collapse. Right? It's not made out of forks, but it's the same idea. So all of that energy goes into heating the star, and that's important because something like the sun has an inside temperature of about 15 million degrees. That temperature comes from this collapse. It's a change of energy from gravity to heat. And you need to have that change because the way that the stars shine, produce all the light of the pictures I showed earlier, is from nuclear fusion. It's a combination of protons into helium atoms. And that requires really high temperatures, 15 million degrees, 10 million degrees, something like that. So stars collapse down to the point where this starts, these reactions start, and then you've got a nice steady star where planets can form around them and life can evolve. Now, as I said, the collapse of stars, so I'm going to do a little physics. It's 8 in the morning. I'm going to do a little physics for you. All right, so if we take our perfect cloud, which is in physics is always perfectly spherical, right, because we keep things nice and simple. This would be a giant black cloud that's about a light year across. As gravity pulls it in, it compresses and it heats up, and the energy is converted into heat. And the amount of collapse depends on how long it takes to get it hot enough to start those reactions. So for something like the sun, start off as a light year across, and then shrunk down to about the size of the sun today. And at that size, it can start making reactions. But gravity depends on mass, and so if you start with a smaller mass star, you actually need to shrink that star even further to get it hotter to do big reactions. And so big stars are big because they can start those reactions much earlier. Small stars are small because they have to collapse down further. So there's a natural question is how small can we make a star? Right? Could I make my cell phone into a star? Right? It could collapse by gravity. How small would I have to make it? Well, you can actually calculate that. Right? It turns out that you'd have to shrink this down to about the size of a proton, and if you could do that, you'd have an android star. Right? But that's not possible. We can't shrink things down to the size of a proton because they're made of protons. Right? So there must be a limit. There must be a limit to how small of a star you can actually have. And this is one of the questions that was asked back in the 1950s and 60s. And it turns out that the answer comes from quantum mechanics, quantum physics. This is Wolfgang Pauli. He's a picture of him back in 1925. He had this idea that about quantum mechanics, about particles, about the stuff we're made out of. And the idea is that no two identical fermions, and fermions are things like electrons and protons and neutrons, the stuff that we're made out of, can't occupy the same quantum state simultaneously. If you want to say this in English, you can't put two things in the same place at the same time. Right? So here's a good example of, this is quantum degeneracy. Here's a good example of subway degeneracy. Right? If you go to Tokyo, during rush hour, they have these sweepers that push you into the subway until you can't get any more in there. And that's it, right? Then they close the doors. So there's a limit to how many people you can stuff into the subway because you can't put 2 people in the same place at the same time. Right? If you could, that would be really good for transportation. So it turns out, not because of subway degeneracy, but because of quantum degeneracy, the minimum size a star can be turns out to be about the size of Jupiter. And if you get down to that size, if you shrink a star to that size, it stops collapsing, which means it stops heating up. It can't get any smaller. It can't extract any more gravitational energy. And at about 7% the mass of the sun, so still pretty small, those kind of objects no longer can start the nuclear reactions that generate the light that we see from stars like the sun. That is the limit for a star. Anything less massive than 7% of the sun doesn't behave like a star, doesn't generate light through fusion. So this was a theory that was developed back in the 1960s, and they came up with a name for this. Actually, at the time, the name was black dwarfs, and then it was Lilliputian dwarfs, and then it was substars, and then it was failed stars. And somewhere along the line, Jill Tarter, who you may know from SETI, if you've ever heard of the SETI project, Search for Extraterrestrial Intelligence, she worked on this as a graduate student, and she came up with the name of brown dwarfs because they change with time. You don't know what color they are, so you might as well just call them brown because that's kind of all the colors. And that kind of saved, she's a theorist, so she kind of saved the prediction for the color. That's why we get the name brown. But it's anything that's less massive than 7% of the sun, and it doesn't act like a star. It doesn't produce fusion. But that means it can have some really exciting properties, because if it's collapsing down to this really dense state, it turns out the density of these things, something like 1,000 times the density of water. And at those densities, you get really exotic states of matter. You get hydrogen that acts like a metal or a crystal. You can compress out water into 16 or 17 different states of solid. There's all sorts of weird physics that happen at these very high pressures and high densities that we can't even reproduce here on Earth. We can't do a laboratory experiment to tell us anything about this. And so these objects were sort of this really fascinating possible way into looking at exotic states of matter. They're also, because they shrink down to about the size of a planet, and because they don't have any energy generation, they get very cold, they actually kind of look like planets. And in fact, they'll look like what our giant planets look like when they first formed. So it gives us kind of a history picture of what Jupiter or Saturn looked like when the solar system was very, very young. But then remember that first question. If there's enough of them, they might be dark matter. Right? So that really drove the search for these objects starting in the 1960s. And so, and then they faded away. Okay, so in the 1960s, no one found it. That's okay. We're just starting off. We'll keep going. 1970s, nothing. 1980s, there was one discovery of one object that people thought was a brown dwarf. It was very exciting. There were 3 conferences about this one object that happened. Turned out it was an artifact on the image. 3 conferences because of an artifact on an image. That's pretty. Science can really work very hard when you have something exciting like this. So 3 decades, nothing. No brown dwarfs were found at all, and many people started to think that maybe these things actually don't exist. Maybe you can't form these tiny little compressed things. Something prevents that from actually happening. And if that was the case, this would be the end of my talk, and I thank you very much for being here. In fact, when I just started, actually when I was an undergraduate here at UCSD, the first brown dwarf was discovered as a companion to a nearby star. So this image is from the Hubble Space Telescope. If you go to the American Museum of Natural History in New York City, the discoverer of this object is actually a curator there, and there's a humongous picture of this. If I was to show you like this seminal, image from brown dwarf science, this is it. Right? This is actually not what the sky looks like. It's not blue and yellow. It's color coded. But this object is the one that we care about. This tiny little thing next to this, what looks like a really bright star. It turns out that little bright star is one of those tiny little M stars that I showed you. So these are tiny little faint objects. And when we took a spectrum of this object, so a spectrum is just taking the light of the star and breaking it up as a function of wavelength. And when you see a lot of structure in there, that's actually a measure of what's in the atmosphere. So this one line here is the spectrum of this interesting little companion. This line here is the spectrum of the moon Titan, which is the moon of Saturn. They look identical. That's really exciting, right? To see this thing that looks like a moon out in space. And it turns out they're very similar because they both have the same molecule in their atmosphere, which is methane. Methane is something that's very common here in biological systems here on Earth. We've never seen it in stars before. Because we've never seen stars that are cool enough where methane could exist in it. So this was really the start of this entire field, to see this object that looked like a planet. How much time I got? 5 minutes, okay. All right, so that was just the beginning. There was a lot of technology that got developed in the 1980s, infrared detector technology. This is an example of one of these kind of like CCDs, except this thing costs about $500,000. I've held one of these things. It's very scary. We put these in large instruments behind large telescopes. We can survey the sky in the infrared. Here's just some pictures of those survey telescopes. We actually had one earlier than the 1980s, which didn't find any brown dwarfs. But more recently, this 2-micron all-sky survey in the bottom right was a ground-based survey. The WISE survey, which has been a satellite that's still in operation, that's around the Earth and taking to the sky in the infrared. All of these surveys have been able to find lots of really faint, cool objects. Okay, this is fun. Okay, so I'll give you a chance to actually find one of these things. This is a not-so-random piece of the sky. It's inverted, so the stars are black and the sky is white, so it's a little easier to see that way. And this is in a wavelength which is visible to our eyes, visible light image. Here's the same field in the infrared. Where's the brown dwarf? Should I go back and... So there's the visible, there's the infrared. Anybody see it? We're looking for the brown dwarf, the thing that's invisible here, but visible here. So it helps if I go actually really fast.
Here it is. The one that is going to
Okay, so, all right, so maybe you've seen it already. I will help. Sometimes it helps when you look in the sky and there's a big circle in the sky, and it shows you where it is. Right? So we go back. That's the infrared image. There's visible image, completely invisible. So this is literally an invisible star. It's a star that has no visible light. You cannot see it in the light that we see with our eyes, and yet there it is, bright as day in the infrared. So we really needed this technology, this ability to look at wavelengths outside of our vision, to see these very cool and very low mass things. So like I said, there's many thousands of these now known. This is just a website that we keep a catalog of them. We classify these objects just as we classify normal stars. We have 4 new classes. Actually, the Emperors I talked about before, we have 3 new classes that have been developed since then. They are also not out of alphabetical order just to keep the whole thing alive. One of the things we like to do with our classes is to take the sequence of spectral types and come up with a good mnemonic to remember it. So, like, oh, be a fine girl, kiss me, less tongue, yuck. Only boring astronomers feel good knowing mnemonics like these. Yawn. I used to like this when I was at MIT. Our buddy Adam feels great knowing Maui likes tops yours. My wife was in Maui, so I got to go early, especially do it in the winter. This was very popular during the election. So anyway, so we've now found lots of these objects, tons of these objects, and we actually think that there's just as many of these brown dwarfs as there are stars in the galaxy, which is phenomenal. We just found them 10, 15 years ago, and now we think they're the same number. So that means, wow, there's a lot of them. They must be dark matter, and it turns out, unfortunately, not. So we take our cosmic scale, which you have to apply for time on the cosmic scale. It's really tough to get. If we take all of the little brown dwarfs that we've found and account for the ones that maybe we don't see because they're a little bit further from the sun, they're a little too faint, and we compare them to all the visible stars that we see in the sky, they are still way too low mass. Right? There may be lots of them, but their masses are tiny, so they don't make up the dark matter. Yeah? So it could be. They could be part of dark matter, but in order for us to have actually found dark matter, we would have had to have 5 times as much mass over here.
Well, that's not what I meant.
Oh,
You're saying dark matter is this unknown quantity.
Yeah.
It would be a fifth of
yeah.
what dark matter is.
Yeah. So it's about 100th of what dark matter is, which means it's not anywhere near enough to yeah. So that's it. No Nobel Prize. Who cares? Well, it's actually, when we start looking at these things in great detail, you find that there's a lot of fascinating physics that's going on in these objects. So, as I mentioned, they're very cold. They look like planets. In fact, they have, not only do they have like the kind of gas we see in stars, but they also have stuff that condenses out of the atmosphere. And it's not like the usual clouds that we see here in the sky of water or the clouds of ammonia that we see in planets. These are clouds of rock. Clouds of minerals and molten iron and just bad stuff you don't want raining on you. Okay? These are actually pretty hot stars, and the first things that condense out are the last things that you can melt, the hardest things to melt, which are rocks and minerals. So in these stars, you start to get these clouds of literally floating dirt. And in fact, not just floating dirt, one of those things that come out of there is corundum at the top. Those of you who are mineralogists know that corundum is one of the main elements for gems, like ruby and sapphire and paparacha. Oh, okay. She would have loved it. Yeah. So there's lots, again, exotic materials in these atmospheres, and this is just literally raining out of the star. Now, when you've got clouds, you've got weather, and we actually do see weather on these brown dwarfs. What we do is we measure the brightness of the star as it rotates around, and we see that there's actually dark sides and light sides to these stars, and as they rotate, we see that those dark sides and light sides change. Their structure changes with time. So we're actually watching the weather on other stars. These things get very, very cold, and in fact, just last month, the coldest of these brown dwarfs were found, and it's about minus 30 degrees Celsius at its surface. This is literally a frozen star. Now, for comparison, our sun is about 6,000 degrees Celsius. Right? So this is literally a place that's frozen. It's gotten so cold it's completely frozen. Very, very different kind of world. And this actually turns out to be one of the closest objects to our sun. So here's the sun. Maybe you've heard of Alpha Centauri, the nearest star to our sun. Probably no one's heard of Barnard's star, which is the second closest star to our sun, which is invisible. But then we've now started to find a whole bunch of other these little brown dwarfs that are literally right in our backyard that we had never seen before. But they are among the closest systems to us. We're also starting to find really weird objects, right? Things that we're not quite sure what to call. And so we find in a very small star-forming cluster in Orion, this is one of the most common star-forming regions that we know, we're finding objects that are, some factor of the mass of Jupiter. So they're like planets, but they're not orbiting stars. They're just floating around by themselves. So are these planets that got ejected from their star systems, or did they form that way? We have no idea. This is a completely new class of things. And the last thing I'll say, one of the interesting things is that if you've watched the movie, this movie Avatar, right? The moon Pandora. If you really read the book, it turns out that moon Pandora is orbiting a brown dwarf. And we actually now think, because there's so many of these brown dwarfs, that perhaps this is a source of planets that may have life around them. Because if you put a little moon next to these things, it's just the right temperature for a very long time to have liquid water on its surface. And that's one of the things that we need for life to exist here on Earth. So I'll just conclude by saying that, what are brown dwarfs? Brown dwarfs are kind of a bridge between stars and planets. They're not dark matter. We're not going to win a Nobel Prize for these things. But we're starting to learn a lot about these two classes of objects, stars and planets, which have been different for all of human history up until about 10 or 15 years ago. Now we're seeing that there's actually a continuum of things between them, because these brown dwarfs are formed like planets, they behave like, they form like stars, they behave like stars, but they look like planets, and they have a lot of properties similar to stars. So the universe is not so simple, right? We can't just put things in these categories that we like to do. It turns out there's a lot more complexity, and brown dwarfs are one of those regions of complexity that we're starting to find that teach us a lot more about how the universe works and what's out there. And I will end. Thank you very much.
Thank you so much for presenting to us today.
My pleasure.
We've made a donation in your name to the Joshua Orphanage in Malawi, Africa. We supplied some school supplies to the kids whose parents have died of AIDS. So thank you again.
Thank you very much. That was great. Thank you.
Rotarians, on your way out, please take the pop quiz that Dr. Bergasser has created. He'll grade them. We'll get your results next week. So,
and I'll get into the time master.
So please, everyone, please rise. Please rise.
Right, okay. You're lucky I can't see the sign. Oh, there it is. Number one.
Is it the truth?
Number 2.
All concerned.
Number 3. And number 4.
Beneficial, all concerned.
Go out in peace.
Thank you, Rotary Serving here, my dad.
Thank you very much.
How do you see the general?
So they're emitting. So when they collapse, oh yeah.
He doesn't get to
Sounds good to me.
Thank you, sir.
Oh, that's like a pleasure.
Well, so yeah, that's we didn't have anything. We were just. That's what happened.
Inside is, yeah, we're doing at some level, the differentiation between play and guitar is blurry, like crazy.
Yeah.
What's the difference between a star and play? There's maybe no differentiation.
And there is a maximum start to go before collapsing. It's the maximum, the biggest start.
Yes, really good stars. They just stars. Essentially, we really burn what's left over is stuff so as long as you have, the sun, as long as you have some nuclear fusion, that keeps the sun. Those things that stays off, a normal size. Yeah.
Yeah.
They don't have enough money.
Yeah.
The first one has, anybody ruled out the fact that there's not
Yeah, so the intercell medium. We can actually we can actually measure how much we do actually know pretty good estimate.
I don't know what's going on.
That's significant.
Mostly my
They put it in line.
this market,
All right, well, I'll let you know.
Okay.
If you need anything else from there, let me know.
All right, I'll think about it and I'll call you. Oh, so let's try to
I'll ask, I already have, very well.
Nice to see you.
It's so fun. It was great too.
It's all business.
Even groceries, this is cheaper.
We have to eat, for a meal or we buy, and we're trying to economize. Right.
Yeah, Michelle did it. That was tough.
So we can have something that's.
She's going.
Okay, very good. So,
The earliest that
actually, I'm not.
eventually we have a spiral and eventually that would be process.
I think she's,
But if you have like
We're
another
gonna get it done in an efficient way.
stirs that up.
sorting out the
So then
seats.
you've got
Sorting out this.
as they get bigger.
It's all business.
It's all business.
Yeah.
In some categories, it's business, you can buy it.
So you're gonna, continental city.
This not paying $1.70.
Exactly.
Yeah, it was funny, like, Amazon is spending $2 million per year for security of
Bezos, Jeff Bezos.
yeah, $2 million. Yeah, but then you think about
So
it.
it's just.
He's a valuable
That's
person.
the first place.
Thank you.
Yeah.
Yeah, and then you will report only 5 people give them salary and some equipment and operations.
That's true. Yeah, look at the
You can learn $2 million.
It's mostly
Yeah, I
about-
tried to get,
think about it, you have
That's why I
24 hours around the clock, every day. That's a lot. So.
Steve, he was,
And there is some interesting economy I don't
But
understand.
the thing that controls the street.
I
I found one
So.
information about our migration because I was puzzled how Bosnia is functioning because it's a dead country. How much money
I have my glasses.
like Bosnia is living abroad send $1,886 million a year to Bosnia. You know, it is pretty much.
1.8 million.
So
That's $2 billion a year. Those 2.69 billion, but in U.S. currency, it's 1.89 million.
Billion.
40 times the size of small ones. Why don't they show up in, why don't you see differences in size to?
You know what is,
Yeah, but this 2.69 billion is billion
Because the size of the stars.
KMs.
but $1 is 1.4, it is like half a euro.
Okay.
Are we just far away from the big
So half a euro is about 60 cents.
So the nearest
Yeah,
star is.
so basically, this is it.
Okay.
So.
And I found another,
That's so, it's like
So they all
one
appear
of the biggest economies is people from the States sending money
So
back.
there's something
yeah,
like.
and in India, they send
Same thing.
$1.2 trillion a year for family help. Can you imagine? 1.2 trillion. You know how, and the Western Union makes like 80% in average.
because they said,
What
well,
they're making out.
actually.
Yeah, they are such a new idea. You know, instead of sending cash,
So you
Good
just
job,
start
thank you.
with your points like this.
Appreciate it.
But then on some of the, I noticed some of the ones that when you had really good resolution, it looked like they were distant. And I thought at first maybe they were movement, but they looked like entire galaxies.
So, like the formation.
From this angle.
Very front, to make them look like.
You mean like that image and the.
No.
Oh, okay.
Keep going back up.
Like these.
That one.
Well, these are galaxies.
Right. Okay.
So those are huge collection stars. So we can resolve those.
Oh, you can't resolve that.
But these are almost all stars, and they look like they have some kind of size, but that's
Yeah.
only the resolution of the telescope. So there's a limit to how sharp you can make the image based on how big the telescope is.
Okay. Got it.
And if you kind of stare at it for a while, you realize that they're all the same size.
That and we're limited by the crystal density in the glass that the lenses and all sorts
Yeah,
of
there's
other
all
stuff.
sorts of limits to
Yeah.
how sharp the image can be.
I have an 8-year-old girl. What do I just go to UCSD to find your
Oh, the physics. So if you search UCSD physics girl,
UCSD
she'll pop up.
Cool.
Yeah.
All right. Thanks again. Great talk.
Thank you.
I appreciate it.
Oh yeah.
One of the better talks. Frankly, if I was 4 years younger and hadn't had a messed up childhood and did better in school, I would have been a physicist.